Hello, my name is Austin Weir. I will be guiding you through the process of characterization of our sensors. This is the final procedure in our sensor production. It is here that we determine the quality of our design and craftsmanship. Here is a simulation of the setup that we use to carry out the characterization process. Our sensors are secured to the stage platform and can be controlled by three-stepper motors to accomplish X, Y, and Z motion. The ATI load cell can detect force and torque in all three directions. The indenter attached to the ATI load cell can also be changed to mimic different shapes and objects when the robot is touching the surface. The flexible sensor can be mounted to one of many 3D printed curvatures. To begin constructing tests, first we will start the stage software. Ensure the stage is turned on and plugged in. Start the user application. Once the software is ready, we will home the Z, X, and Y axes. This is done by pressing the Home button. After the axes are homed, set the X and Y to 2 mm by clicking on the display screen and inputting 2. This ensures the stage can move both forward and backward after alignment. To set up the ATI load cell, first turn on the power supply. Plug in the USB coming from the calibration module, also ensuring that the calibration module is correct for the transducer you're using. A pop-up should appear stating that the device has been detected. This can be closed. Open the ATI software. The first step will be to bias the load cell. After the load cell has been biased, gently use your finger to touch the load cell and ensure it is working and receiving data. We can load a sequence into the stage software. First, click the Move Sequencer tab, scroll down and click Load. There will be presets already saved on the computer. The first preset is named as positive 0.2 to 0.8 mm. This sequence moves the stage as following: 0.2 mm for 3 seconds, then back to 0 for 3 seconds, 0.4 mm for 3 seconds, then back to 0 for 3 seconds, 0.6 mm for 3 seconds, then back to 0 for 3 seconds, 0.8 mm for 3 seconds, then back to 0 for 3 more seconds. We can get ready to capture the load cell data on the ATI software. First click Tools, then Data Collection. Then click the 3 dots to browse for a location to save the CSV file. Ensure you create folders to save the data with meaningful names. For this test, we are shearing the sensor in the X direction with 1.6 newtons of normal force. This is described in the file name. In the data collection screen, the load cell data is described as following in black text. We're ready to set up the capacitance data. First, start serial plot. Refresh the COM port, then select the input you're using. Ensure you have the correct baud rate selected and UART configurations are set up as shown. Click Data Format, click ASCII, and make sure the delimiters are correct for your controller software. Click Open. Press on the sensor to ensure all taxles are working. We're also able to view the live stream data by clicking Enable on the Text View tab. There is a Record tab for capturing data. Ensure the path is correct and the file names are accurate. This will be captured as a text file. For shear tests, I personally like to only view the shear taxles. To do this, go to the Plot tab, hide all channels, then only turn on the first 4 channels. These are the shear taxles. The next step is mounting and aligning the sensor. First, place the piece that mounts to the stage. The max load force on the stage is 10 newtons. Make sure to be careful. Gently mount the sensor with the clamps. Do not fully tighten the sensor until we are ready to align. Apply light pressure to ensure the sensor is properly secured to the surface. Align the sensor as best as possible using the lasers and your vision. Before starting the test, we need to find the displacement values needed to construct the test. In this case, we need to find the Z displacement for 0.1 newtons and 1.6 newtons. This will take some playing around with. 0.63 millimeters is for a force of 0.1 newtons, and 1.28 millimeters is for a force of 1.6 newtons. Record these values in the text document. We're now ready to construct the test. First, apply a force of 0.1 newtons. Start recording on serial plot, then the ATI software. Wait 3 seconds, then apply a force of 1.6 newtons. Wait approximately 3 more seconds and start the stage sequence. If you look closely, you can see the stage moving towards us, following the sequence. Once the sequence is complete, bring the force back down to 0.1 newtons. Stop the load cell data, then the capacitance data. Relieve the force by bringing the displacement to 0 millimeters. Load the same sequence in the Y direction. Change both file names accordingly. Bring the sensor back up to 0.1 newtons. Repeat the same test, but now in the Y direction. These tests can be done with different normal forces, rather than just 1.6 newtons. After this test is complete, we can do the same tests, but now in the negative direction. This ensures all 4 directions of the sensor have been tested. The final results are shown in these 4 images. These images were generated using MATLAB. The first row is the force data during the test. The second row is the torque data. The third row is the change of capacitance relative to its baseline value. And the last row is the change of capacitance alongside the respective force in the shear direction. I would like to give a special thanks to Zi Chen for the animation and to Huron Yin for helping to render the animation. I would also like to thank our project director, Dr. John Madden, and our 2 supervisors, Kieran Morton and Dr. Sakib Sarwar.